Hi everyone, this is Mrs. J, and today we are going to talk about trigonometric identities. Okay, so first we're going to talk about what are called the fundamental trigonometric identities. So these are going to be extremely useful for us when we're simplifying expressions or verifying other trig identities. So these you definitely need to commit to memory. So the first ones are your reciprocal functions, which we should already know. We know that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent, and all of those vice versa. So those we should already know. The quotient identities we also should know. So we know that tangent of x is sine over cosine, and cotangent is cosine over sine, which makes sense because tangent and cotangent are reciprocals. The next three are called the Pythagorean identities, and really they're just kind of different versions of the same thing. So this first one is probably the most common one that you'll see. It says that sine squared of x plus cosine squared of x equals 1. Okay, so if you take this first identity and imagine that you divide each one by, let's say, sine squared. So sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 over sine squared is cosecant squared. So that's how you get this trigonometric identity. So 1 plus cotangent squared of x equals cosecant squared of x. And then again, imagine you took this original one and you you divided both sides by cosine squared. Cosine squared divided by cosine squared is 1. Sine squared over cosine squared is tangent squared. And 1 over cosine squared is secant squared. So as long as you know this first one, you can really derive the other two. But if you have all three of them memorized, it will be a little bit easier for you to recognize different patterns when you're verifying. So make sure you memorize all three of these Pythagorean identities. And the last are called the even-odd identities, and really this is just based on how the graphs look. So for this one, the sine of negative x actually equals the sine of x, and that's because the graph of sine is reflected over the origin, so it does look like this. So again, the sine of negative x is equal to the negative sine of x. So it's going to be the same for tangent because the graph of tangent is also reflected over the origin. If you remember, it looks like this. So these two have what we call odd identities, and then this one, cosine, is an even identity because it is actually reflected over the y-axis. Remember, cosine looks like this, so when you reflect it, it is this. So actually the cosine of negative x is equal just to the cosine of positive x, right? Because we know, okay, the cosine of positive pi over 2 is 0, the cosine of negative pi over 2 is also 0. So the original identities match their reciprocals. So for sine, you could apply the same rule for cosecant. For tangent, you can apply the same rule for cotangent. And for cosine, you can apply the same rule for secant. So these may be useful, that you don't see them as often as the other ones above, but it's good to know that they do exist. Okay, so we're going to start by simplifying trigonometric expressions. So here our goal is to take an expression and create an expression with a single function. So you're going to be given an expression with maybe 2 or 3 or 4 different trig functions, and we want to simplify it to a single trig function. So a few tips. If you are stuck, try rewriting parts of your expression using the identities on the previous slide. So if you see tangent, try rewriting it as sine over cosine. Also, try combining fractions if you can, using common denominators. And last, it's really important to look for alternative versions of the Pythagorean identities. So what I mean by that, here's one of our Pythagorean identities. So it will be really common for you to see maybe 1 minus cosine squared theta, and it's going to be important that you know, oh, that's equal to sine squared of theta. Or you might see again 1 minus sine squared, and it's important that you can say, oh, that's just equal to cosine squared. So it's not always going to be that you see this and you replace it with a 1. You might see alternate versions of any of your 3 Pythagorean identities. Okay, let's try simplifying this first expression together. So here we have cosine of theta plus tangent of theta times sine of theta. So we want to create an expression with just a single trig function. So I'm going to look at it and say, okay, well, what part can I rewrite? And I know that I can rewrite tangent as sine over cosine. So let's try that and see if it opens any doors for us. So we have sine of theta over cosine of theta times sine of theta. Okay, so that gives us sine squared theta over cosine of theta. Okay, so we've managed to eliminate one of the functions, but now we say, okay, how can we go further? So I see that this is a fraction, so I'm wondering, oh, can I create a common denominator so I can combine these into a single fraction? So I know that if I multiply this by cosine over cosine, I now have a common denominator, and that would give me cosine squared theta plus sine squared theta over cosine of theta. And then I know that this is actually one of our Pythagorean identities, and it is equal to 1. So we're left with 1 over cosine of theta, which of course is secant of theta. So now I have simplified this expression into a single trig function, so we're done. Okay, let's try another example together. So here I have sine of t over cosine of t plus cosine of t over 1 plus sine of t. Okay, so here a few different routes we could take. I could rewrite this as tangent of t, but then I'm taking an expression that has 2 different functions and then creating an expression with 3. So just because you can doesn't mean you should. So you can try it, but it might not make the problem any easier. So an alternate route would be to find a way to combine these 2 fractions. So I would need to multiply my first numerator by 1 plus sine if I want to create a common denominator. And I have to multiply our second numerator by cosine. And now I have a common denominator of cosine of t times 1 plus sine of t. Okay, so let's see what that leaves us with. And here I can even distribute this. So I can say sine of t plus sine squared of t plus cosine squared of t is equal to the cosine of t times 1 plus the sine of t. Okay, and now of course I'm looking for different parts of maybe my Pythagorean identities, so I see that this is equal to 1, so I can rewrite it as the sine of t plus 1 over the cosine of t times 1 plus sine of t. And I see here that I actually have a common factor of 1 plus sine of t. So these will simplify, and I'm left with 1 over cosine, which again is secant. Okay, why don't you go ahead and pause the video and see if you can give this first one a try. We'll check our answer in just a few seconds. Okay, so here I started by actually foiling this out. I multiplied the 2 binomials together, and then I said, okay, how can I rewrite these? So I rewrote each term. So I rewrote 1 over cosine, sine over cosine. I rewrote this as 1 over cosine and then sine over cosine. I noticed that these 2 terms cancel out, and then these 2 had a common denominator. And remember, 1 minus sine squared is equal to cosine squared. That's one of those alternate forms of the Pythagorean identities. And then once you have this, well, cosine squared over cosine is just cosine. So you're all set. All right, go ahead and pause the video again and see if you can give this one a try. Okay, so here I rewrote cotangent as cosine over sine, which is why it's cosine squared over sine. I did the same in the denominator. And then I noticed it might be useful for me to clear my complex rational expression, so I multiplied the numerator and denominator by sine. When I did that, this becomes sine squared. Here the sines cancel out, so I'm left with cosine squared, and here the sines cancel out again, so I'm just left with cosine. Remember, this is our Pythagorean identity and is equal to 1, and then 1 over cosine is secant. Okay, so now that we know how to simplify a trigonometric expression, we're now going to move on to verifying trigonometric identities, which is essentially an equality statement. So our goal is to prove that the statement is true, and we're going to do this by picking one side of our identity and changing it until it equals the other side. So we can only work with one side, and again, we just manipulate it until it equals the other side, and you can pick whichever side you want to work with. So a few tips. Look for ways to combine two fractions into one, or separate one fraction into two, so that can be useful. Again, look for alternate forms of the Pythagorean identities. And last, if you're stuck, it could be useful to multiply the numerator and denominator of a term by the conjugate. So remember, the conjugate, let's say we have a term like 1 plus cosine of theta. Our conjugate would be 1 minus cosine of theta. So you change that middle sign. So again, this is just something that you have to know to do, but it can be an extremely useful tool. Okay, so we're going to try this first one together. You might notice as we do these that sometimes we start going down a certain route and we realize that it's not going anywhere. So we have to go back to the beginning and start again. So with these, the most important thing is don't get frustrated. And if you hit a roadblock, keep trying. You'll eventually find something that works. So the general rule of thumb when you're working with these is it's usually best to work with the side that has the most going on, because then you have the most options to change it. So here I'm going to work with the left-hand side, and I'm going to denote that by saying LHS. So again, we're going to only be working with this side, and we're going to change different parts until it equals exactly the other side. So again, this is what we're starting with. Okay, so I look at this and I say, maybe I will try distributing our cosine to the terms inside the binomial. So here that gives us cosine of theta times secant. I can rewrite as 1 over cosine of theta, and then minus cosine squared of theta. So these two statements are completely equivalent. Here, this leaves me with 1 minus cosine squared of theta, which again is a rewrite of that first Pythagorean identity, which is actually equal to sine squared of theta. And so you can see that I've managed to change the left-hand side into the right-hand side. So that means that I have verified this identity. Okay, let's try another one together. So here I'm actually going to choose to work with the right-hand side of the equation just because it looks like maybe there's a little bit more to work with. So when I see something like this, the first thing I'm thinking to try is to combine these two fractions into one, and I can do that by creating a common denominator. So that first fraction, I need to multiply it by 1 plus sine of x over 1 plus sine of x. So I have 1 plus sine of x minus, the second one I need to multiply by 1 minus sine of x. And now I do have that common denominator of 1 minus sine of x times 1 plus sine of x. So again, we are just combining two fractions by making a common denominator. Okay, so now let's see what we have left in our numerator. So we have actually 1 plus sine of x minus 1 plus sine of x. So that actually leaves us with 2 times the sine of x. And then if we multiply out the denominator, we are left with 1 minus sine squared of x. Now, as we're going through this process, remember our goal is to create something that looks exactly like the other side. So we're trying to find a way to make 2 tangent of x secant of x. So it's good because here we see, oh, I have the 2, so now we need to find a way to maybe make tangent. So in the denominator, I notice that this is a rewrite of our Pythagorean identity, and it is actually equal to just cosine squared. So I can rewrite it like this. So remember, my goal is to create tangent. I know tangent is sine over cosine. So if I think of it like this, remember cosine squared is just cosine of x times cosine of x. I can then use this right here to rewrite it as tangent. And then if you look at the rest, I'm trying to make secant, and we know that 1 over cosine is secant. So this can simplify to 2 times the tangent of x times secant of x. And now we're done verifying. So another tip again, as you're going through this process, always keep in mind what you're trying to turn your expression into, because that can kind of give you some hints as to where you should go next. Okay, we're going to try one last problem together, and here I am going to work with the left-hand side just because, again, to me it looks like there may be a little bit more to work with. So remember I said if you are looking at an expression and you're totally stuck, you're saying, oh, there's not really any way I can rewrite cosine, there's not really any way I can rewrite sine, it's not sine squared, so I'm really stuck. One tip that, again, you just have to know to try it would be to multiply by the conjugate. So here I'm going to multiply the numerator and denominator by the conjugate, which is 1 plus sine of u. And let's see if that helps us. It may or it may not, but it's worth a try. So I'm left with the cosine of u times 1 plus the sine of u over, and then in my denominator I can multiply that out and I get 1 minus sine squared of u, which of course we can rewrite as cosine squared. Okay, so now let's look at what we're trying to achieve. We're trying to achieve secant of u plus tangent of u. So if I look at this, I notice that I can actually cancel out a factor of cosine, leaving me with 1 plus sine of u over cosine of u. And then here's that tip of looking for times when you could take a single fraction and split it into 2. So I can actually rewrite this as 1 over cosine of u plus sine of u over cosine of u. And then I see, oh, 1 over cosine is secant, and sine over cosine is tangent. And now that equals the right-hand side exactly, so our identity has been verified. So again, if you are ever completely stuck, try multiplying by the conjugate and see what happens. And also look for times when you can take a single fraction and split it into 2. Okay, here's the last example. Again, please pause the video and give it a try on your own. Okay, so here here's one way you can verify this identity. I chose to work with the left-hand side. So I created a common denominator to combine the 2 fractions. Here I multiplied this out and I multiplied this. What I noticed was going on in my numerator is that I could actually factor out a negative, and then I have cosine squared plus sine squared, which is equal to 1. It doesn't really matter what's going on in our denominator because our numerator has become 1 minus 1, which will always be 0. So therefore, our identity is verified. All right, that is all for today's video. Thank you so much for watching.